All right, here is the key for exam 3 for 2046 this spring. First question, got the pKa of a buffer solution. In this case, it is made out of the weak acid acetic acid and the weak conjugate base acetate. So if you remember, go into here. That means we can use the Henderson-Hasselbalch equation to solve this. And come on. There we go. Henderson-Hasselbalch equation is the pH equals the pKa plus the log of the concentration of the base over the acid. We're told that the pKa is 3.74. We're also told that the pH is 3. So the pH is lower than the pKa. That means for this part right here, the log portion, that has to be some sort of fraction, 0.6, 0.3, whatever, because the log of anything less than 1 will be a negative number. And so to get that, that would mean the acid concentration, what in the doing? That would mean the acid concentration has to be greater than the base concentration, or in their acid in this case is HC2H3O2, and that's greater than the conjugate base concentration, which is the C2H3O2, or the sodium acetate is part of that. Or I guess this was, sorry, this is a different acid. It was HCHO2. Formic acid, I believe it is. Okay. Question 2, we have a 1 liter buffer solution, and now our buffer solution is this acid and its corresponding base, which is a lithium salt. We're given the concentration of those. So what we're going to have is we're adding hydrochloric acid. So we're adding an acid, so that's going to react with the conjugate base. So we're going to get an acid-base neutralization. And when it reacts with that, it'll protonate the conjugate base, and we'll get more of that conjugate weak acid in this case. We can figure out our concentrations. 1 liter times the molarity is going to give us moles. So in this case, we have 0.250 moles of this. For the HCl, it's 1 molar, and we have 0.1 liters, so 0.1 times 1 gives us 0.1 moles of HCl to start with, and for the acid part, that'd be 1 times 0.15 gives us 0.150 moles of our acid. The acid, the HCl, the strong acid, is interacting with the weak base, and we can see that there's less of that. So in our reaction, that's going to be our theoretical yield. Because they react in a 1-to-1 ratio, however much HCl we're going to use up the same amount of the conjugate base there, and then we'll produce the same amount of moles of our conjugate acid. So after this whole thing is done, we'll now have 0.150 moles of our conjugate base and 0.250 moles of our conjugate acid or weak acid. So in terms of our base acid ratio, we can keep these as they are. or we can convert them back into molarity. Either way, the ratio is going to be the same. If we wanted to convert these, we would take our new volume. We had a liter of the original buffer solution, and to that, we added 100 milliliters of that HCl solution. So our new volume would be 1.1 liters. So I could take 0.25 moles for my acid, put that over 1.1 liters. We get, so acid concentration 0.227. And then same thing for the base, 0.15 over 1.1. And that 0.136. So what we have, you'll notice, we had some amount of the conjugate acid, some amount of the conjugate base still, so we can still use our Henderson-Hasselbalch equation. So the pH is going to be equal to the pKa, which is the negative log of 6.5 times 10 to the negative 5. That should be 4.187 plus the log of the base over the acid. So we get 4.187 plus 0.2, or sorry, a negative 0.2222. And we get 3.97 as our pH. Lower than the pKa, makes sense. We've added a little bit of acid. Which of the following is true? Equivalence point is where the amount of acid equals the amount of base during any acid-base titration. That is true. We want to neutralize all of the acid or all the base, both, and end up at the equivalence point. At the equivalence point, the pH is always 7. Not always, it's only 7. We have a strong acid and a strong base. If it's a weak acid and a strong base, or a weak base and a strong acid, it'll be something other than 7. An indicator is not pH sensitive. That's not true. Indicators are pH sensitive. They become protonated or deprotonated and then have different colors depending on that. And a titration curve is a plot of pH versus not the base to acid ratio, but the volume of titrant that we have. Now we have a titration problem here for 4. So we have a 100 milliliter sample of HClO, and it's titrated with 0.1 molar LiOH. Determine the pH after the addition of 50 milliliters of LiOH. So we're looking at this acid-base neutralization, and that's going to give us ClO minus and H2O. And technically it'll give us lithium, but lithium is the conjugate acid of a strong base and won't have any bearing on the pH. And this is a pure liquid, so this also won't come into play here. So I can take my volume times my concentration, 0.1 liter times 0.1 molarity, and see that we have 0.01 moles of our weak acid, and do the same for the lithium hydroxide. It's 0.1 molar as well, but we have 0.05 liters of that, so 0.005 moles of this. So you can see in this titration, we're not at the equivalence point. They're not equal. We have less of the strong base, so we're going to use up all of that strong base. And we'll actually end up producing some of that conjugate base. So here you can see we're going to have 0.005 moles of this left, none of that left, and now we're going to have 0.005 moles of this. So if I have both a weak acid and its conjugate base, what do I have? A buffer, and we can use the Henderson-Hasselbalch equation, again, to figure out what is the concentrate, or what's the pH, sorry, of that buffer. So we're given the pKa or the Ka, 2.9 times 10 to the negative 8. So the negative log of that will give us the pKa, 7.54, plus the log of, and again, we can reconvert these into their molarities, but I'm going to take 0.005 divided by 0.15, and then I'm also going to take 0.005 divided by 0.15. They're going to give me the same number, and again, the same ratio. You'll notice the ratio here is 1, and the log of 1 is 0. So what we have is a buffer, and we have it at the half equivalence point in the titration, at which point it's going to be equal to the pKa. From the molar or the solubility of the ions for the KSP. So what's our KSP equation look like for this? If this is a solid, when we dissolve it and it dissociates, we're going to get 2 sodiums, and we're going to get 1 carbonate aqueous. So if we start, this is a solid, so it gets left out. If we started with 0 of these, we would produce 2 of these for every 1 of these. So that would mean our KSP equation should look like this. Normal equilibrium. And we have 2 of those sodiums, so sodium should be squared. So what I'm going to end up with is 2s squared times s. 2s squared is 4s squared times s is 4s cubed. Which of the following would be the best buffer solution? So not necessarily just a buffer solution, but which one would be the best buffer solution? All right, so for 1, I have HCl and NaCl, but buffers need to be weak acids, ideally, and weak bases. HCl is a strong acid. Even though the Cl minus is its conjugate base, that's really not a good buffer. HBr and sodium hydroxide, this is just a strong acid and a strong base. All they're going to do is neutralize each other. For C and D, I have a buffer. I have a weak acid, and I have its conjugate base, but not the same concentration. So the better buffer would be the one that's higher concentration. It's going to be able to neutralize more added acid or more added base. So the 0.5 molar acetic acid, 0.5 molar sodium hydroxide, or sodium acetate is going to be your best buffer. A complex ion again is when we have that metal, central metal ion, whatever that happens to be. You have a whole table of these. These are your formation constants, your case of F. So you've got, silver complexes and cobalt complexes, etc. So that's going to be that central metal ion bound to 1 or more ligands. And the ligands are the Lewis bases that attach that. Could be ammonia, NH3, could be OH, a whole host of different things. Identify the process in which the entropy decreases. So for the entropy to increase, we would go from a more ordered state to less ordered. In this case, for the entropy to decrease, we need to go from a disordered state to a more ordered state. And the only one here that looks like it's doing that is going from a liquid to a solid. Now, in that case, we're going to be more ordered. And like I said, our entropy is going to decrease, or we'll have a negative delta S. Okay. Here we have, if our reaction is endothermic, and it's accompanied by a decrease in entropy, what can we say about it? So if we go back and we think about our Gibbs free energy equation, I got delta G equals delta H minus T delta S. Well, if it's endothermic, then our delta H is positive. And if we have a decrease in entropy, then our delta S is negative. So negative times a negative is going to give us a positive. So what I'm going to have is a positive plus a positive, which is always going to be positive. And if I want delta G to be negative for this to be spontaneous, then that means it's always going to be non-spontaneous. So non-spontaneous at all temperatures. All right. Below which temperature does the following reaction become non-spontaneous? So same equation, delta G equals delta H minus T delta S. And we want to know when it becomes non-spontaneous. So below a temperature, so at high temperatures, it's going to be spontaneous, but at some point, it's going to be non-spontaneous. So I'm going to set delta G equal to 0. And I know then, as soon as the temperature goes below that, we're going to have a positive delta G, and it will be non-spontaneous. Our enthalpy is positive 136.5 kilojoules. I'm going to convert that to joules because our delta S is in joules, and it is also positive. And then what I can do is subtract this negative 136,500 from each side. Oh. So I get negative 136,500 joules equals negative T times 287.5, and then divide both sides by a negative 287.5. And we get 474.8 Kelvin. So answers 475. Once you go below that, it will become non-spontaneous. So 475.1, you're spontaneous. 75, you're zero. And then as soon as you go below that, it becomes non-spontaneous. Place the following in an order of decreasing molar entropy. So we have NO, PO, and SO. All similar in that we have a single atom bonded to oxygen. So in terms of number of bonds, complexity, that's not really changing. What I would just be looking at here is the molar mass. That should look like this. And in that case, everything else being equal and the mass being the only difference, the one with the highest mass is going to have the greatest molar entropy proceeding to the lowest mass. Calculate delta G for the following conditions. So we're looking at delta G standard is equal to negative 180.8 kilojoules. And we want to find under non-standard conditions, we're showing the pressures, they're not 1 atmosphere. So we want to use this equation right here. So I'm going to have delta G. I'm going to convert that to, again, to joules because our R has units of joules. We are given the temperature is 298 K. And then all I want to do here for Q is set up my reaction quotient. HGO is a solid, so it's good for the products. We're just going to have a 1 up there. And then we're going to have the pressure of the Hg. And in our equation, it's 2Hg, so that's going to be squared. And then the pressure of the O2. So should get, make sure again. Yep, 2,477.57 natural log of 1/6.075 times 10 to the negative 6, which is a pretty large number. Natural log of that is 12.01 times 2,477.57 gives me 29,759 joules. And when I add that to the negative 180,800, I get negative 151,000 or negative 151 kilojoules. Determine the equilibrium constant for the following reaction at 298. So now we, by all indications, do have standard. So what I want to do is set that equal to negative RT ln K. And in this case, my R, again, 8.314. My temperature, 298. We're trying to solve for K. and our delta G is negative 34,500 joules. So dividing both sides by this 8.314 times 298 gives me the 24,000 or 2,477.57. I get 13.9249 is equal to the natural log of k. So I take e raised to both sides, and that gives me 1.11 times 10 to the negative 6. Yeah, or 1.12. Yeah, I guess round. Determine delta S for the following reaction. So on the last page, you've got some constants there. So if I go and I look up the standard molar entropies for everything, I'm going to do products minus reactants. For my products, I'm going to have 3 times my CO2, which is going to be 214, plus 4 times water, and we want liquid water, which is going to be 70. And we're going to subtract from that our products, 1 times for the propane, so 1 times 270, plus 5 times our O2, which was 205. So what we get here is 922. And this is 1295. Gives us negative 373. All right. Which elements being oxidized in the following reaction? So I've got chromium hydroxide, technically chromium 3, and that's plus this bromate. Oops, sorry, not 3, just 1. And that goes to make this chromate here plus Br minus. So the hydroxide's a -1. I can do each of the oxygens and hydrogens by themselves, but since I have that polyatomic anion, I can just figure if the whole thing is a -1, there's 4 of them, that's a -4. Our overall charge is -1, so the chromate here must be a +3. But yeah, each oxygen here would be a -1, each hydrogen +1. Here the oxygen's a -2. If we have an overall -1, then the bromine here must be a +1. Now when we come over to here, I have 4 oxygens at -2 each. That's -8. So if I add a +6 to a -8, I'll get an overall -2, the overall charge for that. And the bromine here is a -1. So we want the thing being oxidized. What's the thing that became more positive? Which is the one that lost electrons. So right here, it's the chromium. Balance the following reaction. All right, so we got Cl2 plus, or not plus, Cl2 goes to ClO3 minus plus Cl minus. So chlorine in its naturally occurring state has an oxidation state of, or number of 0. Each oxygen here is a -2. This chlorine's a +5, and this chlorine's a -1. So chlorine is being oxidized, and chlorine is being reduced. We can pull whichever one out of here that we want first. Let's go ahead and do our reduction. So chlorine 0 going to chlorine -1. First, we have to balance the chlorines. There's 2 on the left and only 1 on the right, so I'm going to put a 2 in front of this. And then if each one is gaining an electron and we have 2 overall, then the total number of electrons gained here will be 2. Now we can set up our ClO3 minus, and that's going to be, sorry. There we go. Our Cl2 is going to be reduced to ClO3 minus. So first balance the chlorines. 2 chlorines on the left, only 1 on the right, so let's put a 2 there. Each chlorine is going from 0 to +5, so we're losing a total of 10 electrons here. Now we have to add waters. We have 6 oxygens on the right, none on the left, so we're going to add 6 waters there. And then that gives us 12 hydrogens that we did not have on the left, or that we have on the left, we don't have on the right. And since it's in basic solution, I'm going to add the same number of OH minuses to cancel out or neutralize all those H pluses. This is essentially 12 waters. So what I can do is get rid of 6 and 6, let's kind of simplify it, and that should be balanced. Now we have to add them. We have to have the same number of electrons. I have 10 in the bottom and only 2 in the top, so if I multiply everything in the top by 5, that'll get it so my electrons can match. Cancel out our electrons. And nothing else to cancel out. That's going to give us 6 Cl2 plus 12 OH minus goes to form 2 ClO3 minus plus 10 Cl minus plus 6 H2O. You'll notice everything here is divisible by 2, so I can simplify this and have a 3 and a 6 and a 1 and a 5 and a 3. And then if we're looking for the numbers in front of the Cl2 and the numbers in front of the OH minus, it's going to be 3 and 6. Determine the cell notation for the redox reaction. So I've got 3Br2 plus 2Fe goes to 6Br minus and 2Fe3 plus. So we're 0, 0, minus 1, plus 3. So bromine is gaining an electron. So it's reduced. And oxygen is losing. Three electrons, so it's oxidized. The thing that's oxidized is our anode, and we want to start with our anode. Iron is a solid, it's a metal, it's conductive, so we can make our anode out of iron. And then we have a phase change to the aqueous component. There's no other aqueous or liquid or gas components involved in that oxidation, so we can add the salt bridge, and then we can look at what are the, make sure I write it the same as it is on here. What are the components or the things being reduced, and what are the things that are gases or aqueous or liquids? So there's my gas, single line to indicate a difference in the phase. There's my aqueous component. Now, bromine is a nonmetal. It is not a solid at room temperature. It is not conductive. So the cathode has to be the last thing on here. And we would use a relatively non-reactive conductive metal as our cathode. The only option on here then that would work is platinum. Using standard health cell potentials, figure out the cell potential for this. So we have lead plus bromine goes to form lead 2 plus and 2Br minus. So get 0 and 0 plus 2 minus 1. Lead is oxidized. And then bromine is reduced. And again, the thing that's oxidized is the anode. The thing that's reduced is the cathode. And I just want to do cathode minus anode. So if the bromine is the cathode, that's a positive 1.07 minus the anode, which is a negative 0.13. So I have 1.07 plus 0.13, which give me a positive 1.2 volts. All right, calculate the cell potential for the following reaction. So you may notice what we have on both in both sides, other than we have that salt bridge in the middle, but I have aluminum 3 plus on my anode side, aluminum 3 plus on my cathode side. So that means the thing that's being oxidized and the thing that's being reduced is the exact same identical reaction. So I want to use my Nernst equation here. Minus 0.0592 volts over N log of Q. Well, if I look up the reduction potential for aluminum and it's on the exact same line, whatever it happens to be, we'll say negative 0.6. If I take a negative 0.6 and I subtract a negative 0.6 from there, I'm going to get 0. We have a concentration cell. Every time that happens, our standard E cell is always going to be 0. We're looking at aluminum 3 plus and aluminum 0. So our N, or the number of electrons that we're going to be transferring, is going to be 3, and then a log of Q. We have the lower concentration being our product, and the higher concentration here being our reactant. So if I take 0.115 divided by 3.89, take the log of that, and we take our 0.0592 divided by 3, multiply that by that, and we're going to get a positive 0.030 volts for that aluminum concentration cell. And then lastly, nickel can be plated from an aqueous solution. How long is it going to take to plate? 29.6 grams of nickel, and we're going from nickel 2 plus to nickel 0. And we used 4.7 amps of current. Some people may have had a different number other than 29.6, but we're going to set it up the same way. We want to find out first, how many moles of nickel is this that we're plating? So we're going to go and look up the molar mass of nickel from our periodic table. Should have been 58.69. So if I divide 29.6 by 58.69, I'm going to get 0.50434 moles. All right, so now I know we need 2 moles of electrons for every 1 mole of nickel. And I know Faraday's constant gives me how many coulombs we're going to get per mole of electrons. I know the amps are measured in coulombs per second. And I know, so I think this is in minutes. Yep. For every 1 minute, we have 60 seconds. So moles of nickel will cancel. Moles of electrons will cancel. Coulombs will cancel. Seconds will cancel if we set it up this way. So, 29 minutes divided by. So if I take that times 2 times 96,485 divided by 4.7 divided by 60, I get 345 minutes, or 3.45 times 10 to the second. But that's everything. Hopefully this is helpful. Speed up the video, slow it down, whatever you want to do, so long as you figure out what the right answer was, wrong answer was, etc. See you Friday.